Welcome to video 11 in a series of introductory videos for SolidCAM. This video's topic is HSS Xpress. HSS Xpress is the basic version of the HSS toolpath, which is included in all software packages from SolidCAM. So even if you have the SolidCAM Express module package, you have the HSS 3D surfacing toolpath. So let's begin. So you can actually access HSS from the SolidCAM operations, HSS, or you can right-click on the operations folder, click on milling operation, and HSS. I mentioned HSS Express specifically for this video because there is a full HSS where you can see here you have full strategies. The rest of these strategies will be actually covered in video 12 of this series. In this video, we're just going to cover the basic one that is available with all packages, which is parallel cuts, linear, and constant Z. So let's begin with linear. Begin by choosing the coordinate system. In this case, we're going to do the back side of the part because it has those tapered faces. Under geometry, this is one of the only toolpaths that uses surfaces to drive the geometry. So you're not choosing a chain or a model. Here you're choosing the exact surfaces you'd like to machine. So we're going to choose drive surface. Let's start with this surface here. Okay. And the area type is essentially how we're going to use that surface. So let me just click on here. In the bottom left corner, you can see that the toolpath will stay exactly inside the surface. It actually will stay within full diameter on those edges there. In this case, I don't actually want that. I want to go to the very exact edges of this surface. I'm using a ball nose. I'd like to take the center right to the tip of that surface. So I can switch it from full avoid cuts at exact edges to full start and end at exact surface edges. And now if we look at that icon on the left side there, it's taking the toolpath right to the edges. I mentioned that as the basic 3D toolpath that you get with all packages, on a very basic package, you might still need to do some 3-axis roughing. And with this toolpath, you can actually use it in a various way to do kind of roughing as well. If you choose to do that and you want to leave some offset on your 3D faces, you do that here under drive surface offset. We can actually put a value in here. Positive value will leave material, negative value will overcut the surface. So you can use that in various ways. Because we're doing parallel cuts linear, I'm actually going to define it by either an angle from the x-axis, or I can define it by a line and 2 points. But today we're just going to go with the default x-axis. Under tool, this is one of the few toolpaths that can use any type of tool in your library. So if you want to use a flat end mill, a ball nose, a bull, a shape tool even, it's one of the few toolpaths that can do undercutting because of its the way that you're defining it using surfaces. You can do undercutting with this toolpath, which means you can use lollipop cutters on this one as well. Because it's being driven by the surfaces, in our level section, we don't actually have a upper level, lower level. What we have is, what we're defining here is the clearance area. So it's either a plane in whatever direction you want, in this case, a plane in the Z direction, or if you were doing turning or some 5-axis, 4-axis work, you can set the clearance area as a cylinder around the part. But because this is 3-axis, we're just going to leave it as plane in the Z direction. The rest of this is defining the retraction height while you're inside the toolpath, the entry and the exit distances, and that plane height from the surface. So in this case, 1 inch above the surface. Under toolpath parameters, we have control over the step over. And we actually define it either by an actual step over, in this case 50 thou, or a scallop height. And the bottom left corner shows us that those are mathematically related. So for instance, if I were to change the step over to 20 thou, we see that the scallop has now changed as well. The remainder of this screen has to do with the quality of the surface. So if you work with translations of step files, IGES files, parasolids, if there's something wrong with the surface, it will affect your toolpath. If the surface was translated with an erratic nature to it, and you want to just kind of reduce the tolerances of that surface, you have the slider, or you can put in a value here, and all this is really just to control the quality of that surface, how closely you follow that surface. Tool control doesn't really come into play with the 3-axis toolpath such as this one. You'll see this used a lot when you use HSS in a 4th or 5th axis toolpath. This really just controls the angle of the tool, or in this instance here, it just controls what we use as the contact point along that tool. I suggest leaving it at auto unless there's a specific need for your tool to follow just the center of the tool or just the radius of the tool and whatnot. The Link tab allows us to control the entry and the exit of this toolpath. So as soon as it gets to the surface, it's going to be driven by the surface itself. But before we get there, we can either enter from the clearance area, the retraction distance, the safety distance, and so on. And likewise for the exit, you have the same option. You can choose to use a lead in, lead out to enter that surface. So again, don't use lead in, lead out, use lead in, lead out. Under the Links tab, we have control over what happens inside of the toolpath as it's following that surface. So if there's a gap along the cut, these are the directions as to what to do when it encounters a small gap and a large gap. And to determine what is the difference between a small and a large gap, we have a percentage of the tool rating right here, or you can set it up as a value. Again, likewise, if we wanted to use a lead in, lead out as it goes in between those gaps, you can put that here. Links between slices, that is the gap that occurs at the end of the path. So say, for instance, we're going along the surface to here, and we're going to reposition so that we can go backwards. Say we're doing a zigzag. Well, we can tell it what to do when it gets to the end of the surfaces as well, to link those slices. And again, difference between small moves and large moves is dictated by a percentage of the tool. I mentioned a lot about using lead in, lead out. We actually define which lead in, lead out to use here. And again, because this is a 3-axis toolpath, we'll have various options on how to lead into or lead out of the part. As soon as you choose one of the options here, let's say we go with the default of tangential arc, you have options here of the parameters related to that. So for instance, tangential arc, we have the arc sweep, and we have the arc diameter. Because the toolpath is being driven by surfaces, it doesn't actually pay attention to the rest of the model. So we can put in here a gouge check against anything nearby. So all I have to do is enable the gouge check. It'll gouge check against the holder, the arbor, the tool shaft, and the tool tip. Oftentimes, I'm just going to be checking against the shaft and the tip. That's in my SolidCAM settings, how I set that up. And you can go back to video 1 to see how I actually set that up. We're going to be gouge checking against the drive surfaces, which are the surfaces that I selected in my geometry section. And I can also gouge check against check surfaces, which I choose here. And I can actually do so by either individually choosing the surfaces, just like I did in the drive surface section, or if I want to make it simple on myself, I can say add all the faces adjacent to those surfaces. So any faces that are touching my surface have been selected when I click that button. What we do when we encounter those check surfaces, those gouge surfaces, is under strategy. So we have 4 options here, the first of which is Retract Tool. So if the tool is going to encounter one of those check surfaces, it will retract along whichever direction I choose from this list. The default setting is the tool axis. Second option is Trim and Relink Toolpath. So this will continue the toolpath in the intended direction, but it will remove the part of the code that was going to collide with those surfaces. And we can tell it which part of the code to actually remove in this submenu. So collision only, if you see on the left side here, will remove the bit of the code that is only bit of the code that's colliding with the check surfaces. The other options are removing other bits. So for instance, here it removes everything after the first collision, everything before the last collision, everything in between the collisions, removes everything except for removes everything before the first collision, but it trims the rest of it, or the opposite. Removes everything except for the last collision. It just leaves it, it trims out the entire line. I often like to just suggest to customers using the Trim and Relink Toolpath, trim collision only, because that will result in the actual surface being machined, and it trims out only the bits that are going to collide. Okay. And lastly, we have roughing and more. I mentioned before that this is a toolpath that is provided on all levels of our software, meaning that even on the basic one, if you need to do a 3D roughing toolpath, you have the ability to do that here by selecting the surface and then telling it how many radial steps and how many axial steps you'd like to take to machine that out. Okay, so let's take a look at what this looks like. Save and calculate. Now, I did a linear toolpath. Let's just go back here, with 0 degrees from the x-axis, which means the tool is actually zigzagging back and forth along the x-axis. And we can see that when it got to the gaps and the edges, it's retracting to the clearance area. So I usually tell customers, generate the toolpath, see where that pops up, and then you can go back to your Links tab to refine it a little bit. Let's make this a better toolpath. So I don't want it to retract to the clearance area at the slices, because that's useless motion. So let's go from clearance area to follow surfaces. And I'll just calculate that so we see what that does. So each one of those slices, we just added a feed movement. And rather than going to the clearance area, wasted retraction motion, it's actually just going to follow the surface and continue on. And that looks like a very nice looking toolpath. But what would happen if I had switched it to going along the y-axis, or in this case, 90 degrees from the x-axis? Well, it's going the long way along the surface. This is probably the way I'd actually like to do it because it looks better for the surface. But now when it encounters those slots, it wants to go to the clearance area. So again, let's go to Link, Links. That's a large gap. Let's change that to Follow Surfaces. Okay. In that case now, we get a nice looking toolpath that just enters from the top, zigzags back and forth. Even if I had not already removed that slot, if I had just maybe semi-finished it, or it's still there. I want to finish this entire surface, and I don't want to go to the clearance area. I now have finished even that surface in there. So again, nice looking toolpath, no wasted motion. So that is the Parallel Cuts linear toolpath. Let's take a look at all these parameters, but how they apply to the constant Z toolpath. So save and copy. I'm going to turn off the toolpaths from the previous one, and let's switch this copied toolpath to constant Z. So all my parameters are the same, start and end at exact surface edges along that same surface. But in this case, I don't have anything dictating the direction. It's a constant Z toolpath, meaning that it's going to slice up that surface in the Z axis, and it's going to look more like a waterline cut. In my toolpath parameters, I'm still going to do it as a 20 thou, but this time it's not 20 thou along the surface. It's actually 20 thou in the Z direction. And we'll see how that applies to a surface that has a very shallow slope, such as that one. So if I do a save and calculate, we'll see the difference between a linear and a constant Z as it applies to this toolpath. That is actually not a good toolpath because you can see that it's very spaced out. That's because the 20 thou, as I mentioned, is in the Z direction. So those two lines of code, those two lines of passes are actually Z.02 away from each other. But if we look at it from top view, that actually fans out a little too much. So for this toolpath, I probably wouldn't actually use a linear tool, a constant Z toolpath. So that is how you distinguish linear versus constant Z. Constant Z is really good for very steep draft angles, very curved surfaces. I could even use it for the outside edge of my part if I want to, if this wasn't completely vertical and I would want to use a profile toolpath. So if you have any questions on these particular options from HSS Xpress, or any questions on anything else in these videos, you can call us at the main tech support line at 1-866-975-1115, extension 2, or you can watch the rest of the videos in the series. Thank you for watching.